On June 12, 2025, one of the world's safest aircraft took off under a clear sky. Within just 30 seconds, it vanished from the radar, exploded into a college hostel, and left behind nothing but smoke, rubble, and questions. Flight 171 wasn't a typical accident. It was the first time a Boeing 787 Dreamliner had ever gone down in a fatal crash. A plane known for its perfect safety record, equipped with brand new engines, flown by trained pilots, and surrounded by flawless weather conditions, somehow fell out of the sky without warning. But what scientists just discovered inside the wreckage changes everything. Because buried within the flight data and confirmed by black box recordings is a finding so disturbing, so unexpected, that it doesn't just point fingers. It destroys Boeing's most trusted aircraft program. This isn't about a missing part or a tired pilot. This is about something the aircraft did or didn't do that no one at Boeing is ready to admit. And what you're about to hear will change how you see flying forever. Before diving into what failed, we have to look at what should have worked. Flight 171 was powered by two General Electric GX-1B67 engines, among the most reliable jet engines in commercial history. The right engine had just been replaced 3 months prior. The left one had passed all maintenance checks and wasn't due for service until the end of the year. On paper, the propulsion system of this aircraft was bulletproof. Not only were both engines certified and inspected, but they had no wear indicators, no oil pressure anomalies, no vibrations, no overtemps. Clean logs, clean systems, clean record. And that's exactly what makes this crash so confusing. Because within seconds of liftoff, both engines lost power. Not one, both. A complete flameout, a full shutdown. Something that experts in aviation call virtually impossible. In commercial aviation, dual engine failure after takeoff is considered one of the rarest events. But what the investigators found wasn't wear and tear or a broken component. What they found was a perfectly built machine that somehow stopped flying anyway. When rescue workers found the wreckage, one component caught their attention immediately. The ram air turbine, or RAT, had deployed. For those unfamiliar, the RAT is a last resort device. It only appears when the aircraft has lost all engine power or total electrical failure. It's a tiny wind-powered turbine that spins to generate just enough electricity to run the most basic systems: emergency hydraulics, flight instruments, and communications. The RAT is not supposed to be seen during a normal flight, especially not 30 seconds after takeoff. Its presence meant that the aircraft had entered a full emergency state long before any distress call was made. When the black box was recovered from the rooftop of the building, investigators saw it too: full power drop. No prior warnings, no flameout signal, no gradual decay of thrust, just a sudden and total shutdown of both engines. And that's where the science began to push back against the assumptions. Because RAT deployment is binary. It doesn't lie. It's either there or it isn't. And if it deployed, then the aircraft was already dying before anyone could do anything. To get answers, Air India's senior pilots recreated the entire takeoff in a full-motion Boeing 787 simulator. They tried everything: flaps misconfigured, gear left down, throttle mismanagement, even incorrect speeds. Each time the simulator climbed. Each time the aircraft kept flying. Even with multiple faults introduced, the Dreamliner refused to crash. That alone raised alarms. Because if every known variable failed to reproduce the accident, then what caused it? The simulator wasn't the only thing that failed to recreate the disaster. Software engineers fed the flight data into automated systems and discovered that the crash only made sense if both engines were manually or digitally cut off simultaneously. But why would anyone do that? Neither pilot had a history of instability. The CVR recordings showed no panic, no struggle, no screaming, just confusion. One pilot reportedly asked, "Why did you cut off?" The other responded, "I didn't cut off." That's when experts realized the crash may not have come from the pilots, but from the system itself. Some experts believe the cause lies not in the hardware, but in the software. Specifically, in the aircraft's engine control systems, an intricate network of digital signals that determine fuel flow, throttle response, and combustion timing. A single faulty sensor, a corrupted input, or an invalid data stream could have caused the system to believe the engines were overheating or misbehaving. and shut them down in response, automatically, without a warning, without a human override. This kind of behavior is not unprecedented. In the Boeing 737 MAX crisis, faulty angle of attack sensors caused the MCAS software to push planes into fatal dives, despite pilots fighting the controls. In Flight 171, the suspicion is similar, that the FADEC system, or a related component, received faulty input and issued a shutdown command without confirming its accuracy. The engines, trusting the data, obeyed. And the result? A perfect aircraft, perfect weather, perfect flight. That collapsed because the logic was flawed. Not the metal, not the crew, but the assumptions built into the software. As engineers dove deeper into the black box data, they found a line of code, simple, overlooked, and terrifying. Logged milliseconds before the shutdown was triggered, the FADEC recorded, "Mode transition not acknowledged." This phrase meant that the aircraft's engine control system had attempted to shift from ground idle to climb thrust, and the request was denied. Denied by whom? Denied by what? The engines were ready. The throttle was engaged. The altitude was rising. But the command to go full thrust was never accepted. That sentence, "Mode transition not acknowledged," implied something unthinkable, that the system didn't believe the aircraft was flying, that despite positive rate of climb, gear up, flaps deployed, and speed increasing, one critical sensor, or software line, reported no liftoff. As a result, the engine logic remained in ground mode, where power is restricted to prevent damage during taxiing or aborted takeoff. And when full thrust was requested, the software saw that command as invalid. It didn't reject it with a warning. It didn't sound an alert. It simply did nothing. And in an aircraft designed to react instantly, this stillness was fatal. The engine shutdown theory led investigators to a single point of vulnerability: the WOW system, weight on wheels. This sensor tells the aircraft whether it's in contact with the ground or airborne. If the WOW system falsely reports on ground while the plane is in flight, it can block certain flight phase-dependent functions. And that's exactly what some scientists believe happened to Flight 171. If the WOW system malfunctioned or failed to transition, the FADEC would behave as if the aircraft never left the ground. It wouldn't allow full engine power. It would ignore climb logic. It might even initiate engine protection routines designed only for ground roll. The irony? The aircraft would think it was protecting itself by shutting down. And what's worse, this failure mode had been theorized before. Previous minor incidents with WOW switches had been dismissed as quirks, temporary logic errors, never fatal. But Flight 171 made it clear that the threat wasn't theoretical. It was real. And it had gone unpatched for over a decade. Boeing never issued a bulletin. No airline was warned. And now, a Dreamliner was dead. Internally, Boeing responded to the preliminary report with what appeared to be carefully crafted language. No admission of system error, no acknowledgement of software vulnerability. Instead, they praised the pilot's professionalism and committed to supporting a full investigation. But outside the press releases, whispers began to spread. Former Boeing engineers leaked that the FADEC system had long been criticized for lacking redundancy in phase detection logic. Others revealed that Boeing had refused to redesign critical sensors like WOW because it would cost too much, delay delivery timelines, and require recertification. Scientists within aviation boards urged an emergency review of the 787's logic control stack, but no directive was issued. And when investigators requested full FADEC code access for independent review, Boeing refused, citing intellectual property rights. To the public, this was a technicality. To experts, it was a red flag. Because if a system failed without alerting the pilots and the manufacturer wouldn't let others confirm how, then transparency was gone. And trust, once broken, rarely returns. Weeks after the crash, a small team of analysts from Europe ran their own simulations using an exact clone of Flight 171's digital profile. They introduced a WOW sensor failure during takeoff, then blocked the mode transition, then issued a thrust command. In every case, the result was identical to the crash profile. Engines idled, power restricted, RAT deployed, relight delayed, altitude lost, impact, Unavoidable. And then came the final blow. In one test, they triggered a manual override, exactly what the captain of Flight 171 had done. The relight worked, but only on one engine. The other, having passed a software-defined idle limit, would no longer spool up, not because of damage, but because it had timed out. In other words, the Dreamliner had a digital expiration, one where, after too much time in the wrong logic mode, recovery became mathematically impossible. What scientists discovered inside the data wasn't just an explanation. It was a warning, a blueprint of a perfect aircraft undone not by metal fatigue or explosive force, or even a rogue pilot, but by the quiet certainty of a system that simply refused to change its mind. Flight 171 didn't crash because of a mechanical explosion or pilot error or weather or sabotage. It didn't crash because something was broken. It crashed because a machine believed something that wasn't true, and no one, not even the pilots, could convince it otherwise. In those final seconds, a multi-million-dollar aircraft, flying under clear skies, with perfectly functional engines and two capable pilots, died not from chaos, but from certainty. The aircraft thought it was still on the ground, so it refused to climb. It rejected full power. It dismissed emergency commands. It followed its logic without hesitation, without fear, without pause, because the system wasn't built to ask, why? It was built to trust the data, and that trust, in a single corrupted signal or invalid transition, became fatal. Boeing didn't program the plane to crash, but it did design a system that had no room for doubt, no redundancy for faulty logic, and no override for a lie. The engineers never imagined a moment where the aircraft would be airborne but digitally grounded, and that blind spot cost 242 lives. What scientists discovered inside Flight 171 wasn't a malfunction. It was a system that worked too well, a machine that obeyed too quickly, and a logic chain so airtight that once the mistake began, nothing, not even truth, could stop it. This wasn't the collapse of an aircraft. It was the collapse of Boeing's most sacred assumption, that their machines would never need to question themselves. And now, with trust shattered, with questions unanswered, and with black box data confirming what no one wanted to admit, Flight 171 has become something more than a crash. It has become a mirror, a reflection of what happens when perfection refuses to listen. If this story shocked you, if it made you question who's really in control when you step onto a plane, don't let it vanish like so many others. Subscribe for more in-depth investigations into the truths hidden beneath the surface.